Yes, sir. We can start. We go to live. Start now, sir. Please.
Okay. Good afternoon, ladies and gentlemen, and fellow colleagues. I'm going to be giving the keynote talk today and chairing the session on challenges with tailing dams. A bit of my background. My name is Harvey McLeod. I'm a principal with Clone Cripp and Berger in Vancouver, Canada. And as graduate from in engineering geology and soil mechanics from the University of London, and I have over 45 years experience with tailing dams all over the world in over 26 countries. And I've been very active with Icold. In fact, one of my first Icold meetings was in India over 20 years ago. I was instrumental working with the government into the investigations on Mount Polley and development of guidelines for dam foundations with the government of British Columbia. And as chairman of the Icold committee, we lead developing and writing bulletins for better dams for society. So my talk today is going to, and I'll share my screen. Just one moment. I guess first of all, it can, and I'll go into presentation mode. Can everyone see my screen fine?
Yes.
Okay. So my talk, I'm going to be talking about the about tailing dams, the engineering challenges and safety aspects with tailing dams. And some of the key things I'll be covering are why do tailing dams fail? Some of the challenges with upstream dams, and also understanding upstream dams. We'll discuss some of the challenges with risk assessments and credible failure modes. And how do dams fail and why do they fail? And you know, you've seen the major catastrophes recently. What happens when a dam fails? Does every dam fail like Fundao or Feijiao? And then I'll move into why are tailing dam breach analyses different for tailing dams than they are for water dams. So just some examples, and I'm sure you've seen these quite a bit. But if you take centerline and downstream tailing dams, essentially they're engineered structures, and often the failures are associated with similar causes that you may have with water dams. On the left there, we have Asno-Kolar in Spain that failed, I think almost 20 years ago. And it failed on a weak clay shale layer. This region of Spain has the Guadalquivir clay shales, and every 20 or 30 meters in the clay shales, you get a weak bentonitic layer. And the dam slid on that bentonitic weak layer. Similarly, Mount Polley, it's in a glaciated environment in northern Canada. And these glaciated environments, just by their very nature of receding and progressing, can form lakes within the glaciers or on the edges of the glaciers. And some of these clays that are deposited, some are heavily consolidated from high ice loading, and some are lightly consolidated. And basically, Mount Polley, the dam failed on a less consolidated layer, and that exceeded the pre-consolidation pressure, and it failed. But other dams, and these are some examples of centerline dams. You see the very dramatic one of Feijiao in Brazil. You know, it's quite frightening. Basically, failed in seconds. very catastrophic. And that would be, if you like, the extreme edge of what happens when a dam fails. The other two examples that you see there, there's Cadia. That was in Australia, just happened, I think the year before last. And a very similar one, Sullivan in Canada. That one happened in the 90s. Both of these dams, the tailings liquefied, and you had some flow, but it was not a catastrophic release. So you can have liquefaction of tailings, and in some cases it may lead to deformation of the dam, such as those two, or it may lead to a catastrophic failure. And my talk will get into some of the background as to why. Also then is the other component, or other loading, is the seismic. And I put this one here, it's El Cobre in Chile. It's a cross section that shows before the quake and after the quake, but it does show that not 100% of the tailings failed. All of the tailings did not liquefy and flow. Certainly the upper 20 meters of the tailings failed, and it did fail catastrophically. So it's not to say they don't fail catastrophically, but the lesson here is that how much of the tailings are involved when a dam does fail. The other examples for dam failures, common, are the overtopping, and whether it's an upstream dam, centerline, or downstream dam, overtopping, if you don't have the adequate flood design, or it's mismanagement of the pond and freeboard, you can get overtopping. So to me, I would call that more of a conventional engineering problem and a construction operation problem. So I mentioned, the centerline and downstream dams, often, if there are failures of those are due to typical engineering deficiencies, lack of site investigations, missing something in the design, maybe on quality control. But upstream dams, they rely on the properties of the tailings, because the tailings themselves are forming the structure of the dam. These are slides that we took from our Icold bulletin, and you'll see on the left here the upstream dam with the red line. Basically, everything to the right of that red line is a structural zone. It's the dam, and that dam has to withstand all the potential loading. And traditional upstream dams, they rely on the properties of this tailings. And when you combine that with the potential engineering deficiencies, you generally have a greater degree of uncertainty with upstream dams. Modified upstream dams, as you see over here on the right, where you basically add a buttress to the slope to take advantage of the strength of the fills here to compensate for the strength or the potential lower strength of the tailings. And certainly we're seeing more variations of this these days as people realize the uncertainty with tailing dams. But importantly though, tailings, they have a wide range of geotechnical properties, and they're due to the ore type, the processing, and deposition methods. So here, this is from our Icold Bulletin 181, Tailing Technology Update. And we have the tailings classified from coarse tailings all the way to ultrafine tailings. Excuse me. So you take a coarse tailings, it's almost like a sand. It comes from very hard rock, and we grade into hard rock. It's more like a sandy silt, generally low plasticity or non-plastic. And then we start moving into altered rock. So these would be ore deposits that have some alteration or some weathering of the rock before in the processing. So they have some clays, starting to get into plasticity. Then you move into fine tailings with more plasticity and what we call the ultrafine tailings. And we have characterized these 5 different levels in the bulletin and give you some basic understanding of their geotechnical properties. But one thing I think I really like to relate to people is that you can get a good understanding of your tailings by what we call the simple jar test. You just take like a 500 milliliter beaker, take a sample of your tailings, mix it at 50% solids by weight, and shake it up. And then you measure how much it settles and what the percent solids concentration is of the solids. And you plot it on this chart here, which has solids concentration, and on the horizontal axis, it's settling time. Generally, most tailings settle within hours, some in a day or two. If you get into ultrafine, some of these tailings can take weeks, months, years to settle. I've had samples down here which have been on my desk for several years and still haven't settled. And this basically gives you an idea of the initial settle density. And you can see for specific gravity 2.7, that translates to a void ratio of 1 if it's a coarse tailings, all the way down to void ratios of 4 and 5. So you can see there's a lot more water in these fine tailings. And that is an important consideration when we come to looking at how the tailings behave, and particularly in a dam breach, how would they behave? The other important challenge that we have with tailings is that it's a very heterogeneous deposit. It's spigoted out. There's variations in the spigoting rate, variations in the processing, and you get a combinations of fine and coarse materials. So this is a plot using the cone penetration test data where we plot the normalized cone resistance, QT, against the normalized friction ratio, pardon me. And these relationships were developed primarily by Robertson over the years. Peter Robertson, know him very well. And it's basically saying, you can see with this wide scatter of data that you have a huge variation in the properties of your tailings. So as a designer, what are you going to pick? The average, the lower bound, somewhere in between? And this gives you a good idea. Now, this is, I'm not sure in terms of soil mechanics, how familiar everybody is, but it's called a critical state line along here. Basically, material plotting above it is dilative, and every material below it is contractive, and it tends to collapse when strained. Now, it's interesting when we consider the Fundau slimes, and I mentioned, why does those Brazilian dams fail so catastrophically? Some of those slimes are plotting way down here, well out of the range of typical properties, which are generally up in this range. So understanding just what are your actual properties of your tailings and their distribution within the structural portion of the dam is critical. And understanding these properties with respect to how they might behave in a dam breach is important. So what properties may indicate susceptibility to flow liquefaction? Well, certainly the higher void ratios in the associated liquidity indices. Liquidity index, your moisture content minus the plastic limit divided by the plasticity index, are critical indicators. Terzaghi in 1948 basically said, liquidity indices over 1, the material tends to flow. Well, some of the Fundau slimes were liquidity indices up to 2. And some of the quick clays that you get in Canada, the marine clays, you can have liquidity indices of 5, even up to 10 or 15. So understanding the liquidity index, the in situ liquidity index of your tailings is an important indicator with respect to its potential susceptibility to flow liquefaction. The other one is almost universally, tailings are contracted. They're, 95% of the time they're in a loose state, and they will behave as an undrained soil unless they become unsaturated. And some have been able to densify it. One of the mines in Canada actually have dozers on the tailings beach and densify the tailings, but that's pretty unusual. And so when it's forming part of the structural zone of the dam, you have to look at the undrained factors of safety. It's not Safety is not controlled by the drain strength, it's controlled by the undrained strength. As a contractant material, that's how you have to assess it. And so many assessments are not or have not historically considered that very well. Now, the other part I want to talk to you today about is, what can go wrong. And we've been doing risk assessments for years. I think this one here, I developed that in the 90s with the U.S. Forest Service. Semi-quantitative failure modes effects analysis, which is very common. And it's used more in the water dam industry, qualitative risk assessments and event trees. It's starting to be used more in tailing dams. And these risk assessments, they're good for identifying preventative design options, thinking about what could go wrong, and thinking about how you could, as I mentioned, with design or with operations, reduce your risk and generally move them from the top right corner to the left. But what are some of the weaknesses of the risk assessments? And I've been, in the last 5 years, I've looked at over 150 tailing dams and risk assessments for them all. And there really is a danger of simplifying failure modes. Yeah, some will say, well, the dam could fail by seismic, without really understanding what is the mechanism of the failure. How is it actually going to fail, right? As opposed to just assuming that an earthquake could fail a dam. And the other one, particularly with the qualitative risk assessments, I think it gives a false sense that we can actually calculate the probability of failure and tell people that it's, 4.56 times 10 to the minus 9 annual probability. Well, I think we're kidding ourselves with a lot of these numbers. So we do have to always sort of go back to this mechanism of a failure. And it's much more important to understand the potential mechanism and just focus on what is a credible mechanism that could lead to a failure of the dam. So here's an example. So to be specific, people will say, well, if the pore pressure rises, the dam will fail, and that's the risk, and we give a probability to it. But really, how does it rise? Is it due to rainfall? Is it due to loading? And what's the reason for it rising? And if it does lead to a lower factor of safety, does the dam collapse or slump or settle? What happens? And I've seen cases where you have a rockfill dam. How could pore pressure possibly rise? In that case, does it even matter? So I think it's better to spend more quality time on a few failure mechanisms than to have a failure modes effects analysis or a qualitative risk assessment that has 100 events in it. So understanding this credible failure modes, it's a critical aspect in understanding the consequence of a dam failure. And the Global Industrial Standard for Tailing Management, they came out with their standard August 2020, and they have introduced the terminology of credible failure modes, scenarios, and catastrophic failure. And this is really addressing the issue that tailing dams are different than water dams. When a water dam fails, all the water is going to get released. When a tailing dam fails, you don't know what's going to happen if you don't understand the properties of the tailings and how it will fail and what will the consequence be. So it's a very important consideration with tailing dams because, as I say here, it contains basically lightly consolidated soil. It can have a wide range from the Feijiao to Cadia or Mount Poly consequence. So dam breach methodology for tailing dams, and this has been evolving. It's still evolving, and to date, a lot of the assessments have been dominated by water dam practices and hydrotechnical engineers, and not geotechnical engineers. And the methods currently being used, they virtually ignore the geotechnical properties of the tailings and try and fit it into a water dam type failure. And there's no evidence to suggest, 100% of the tailings will liquefy and flow as a Newtonian fluid. So who's making these decisions in the dam breaks? Are they hydrotechnical engineers deciding how much is going to fail? Is it going to flow as a Newtonian fluid or a non-Newtonian fluid? And so if you step back and say, well, a dam breach, really we have two mechanisms, if you want to simplify it. The first one, you have water transported tailings. There's no question if you have a certain quantity of water, it only has the ability to erode so much tailings. And I think over the last probably 10 or 15 years, I've been using this rule of 1-to-1. If you have a cubic meter of water, it could erode a cubic meter of tailings. Physically, it just can't erode much more than that. And there has been a recent reassessment of historical dam breach failures, and it'll be published soon. It shows some correlation like this as well. But these, and it's been a problem in our industry where the numbers people are getting are from historic correlations. And I kind of use the analogy that, if you went out and you got 100 different types of fruit and you took an average of all those fruits, and you said, well, this is what a fruit is, it doesn't make any sense. And it's the same with tailing dams. You've got all these different types of tailings, and yet people are taking all these failures of all these different types of tailings and coming up with an average correlation, which it's so severely skewed that you really have to question if it has any value. But the second one, and this is the one that really has a lot of uncertainty in the industry. Okay, the water has washed away the tailings, but is the rest of the tailings going to liquefy, as it did in Brazil? And it's back to this understanding of the liquidity index and void ratio. And also understanding, both Cadia and Mount Paul, both Cadia and the Sullivan site, they had some partially saturated tailings, and that influences how the dam fails. And if we look at seismic liquefaction, it's also controlled by the tailing properties and the seismic response. But as you mentioned earlier, even in those, the major failures in Chile, not all of the tailings fail, just the upper 20 meters. And so we do have people today saying, well, we have to assume everything will statically liquefy, where even with large earthquakes, everything doesn't liquefy. So this understanding of what can liquefy and why will it liquefy, and the understanding of the water transport are basic principles of the dam breach understanding. So the current practices, they're based on assumptions of how much tailings that might move. Some assume a percentage of the total tailings, which, as I mentioned, it doesn't make any sense. Another one assumes the geometry of the fail slope. And unfortunately, some of them assume that the back slope of the tailings will be the same as the liquefied material that's flowing downstream. But the back slope at Mount Poly, for example, was more like 25 degrees. And so this angle could be anywhere from, 4 degrees to 25 degrees. And so how do you pick an angle? So both of these require some basic assumptions, which are to me are flawed, and really the person has to go back into the understanding of the material and how is that going to develop that. Because really the in situ properties, tailings are consolidating. At the go towards the base of the tailings, the yield stress increases with depth, and so the behavior of the tailings with depth changes dramatically from the surface of the tailings to the base, and understanding that variation in yield stress is important. So the credible dam failure consequence, it's critical to communicate to regulators and to people what happens when the dam fails. So I think it's very important that we get this right, that we do get an understanding. And we want to move towards safe tailing dams for closure, and we have to understand that if we remove these failure modes, that they are safe for closure. So this understanding is critical to closure of tailing dams as well as it is to the operating of tailing dams. And traditionally, the minimum flood and seismic criteria should align with the consequence classifications. And certainly, a number of companies and the global standard are suggesting that we should always use the higher loading criteria, recognizing that a dam failure, no matter whether it's small or big, has a significant potential effect on, you could lose 100% of your shareholders' value, and you could kill someone. And so the selection of the design criteria, while it follows the conventional water dam, I think there's other considerations that you need to take into account when selecting your design criteria. So what happens when the dam fails? Is everyone a Fundau or Feijiao? No, I don't think so. I think those dams were unusually susceptible to liquefaction. Some, especially the finer slime portions, were highly sensitive and brittle. And there are thousands of safe upstream dams. At the same time, I think many of them are not as safe as many people think they are. And many dams fail without catastrophic consequences. So in summary, tailing dams are different than water dams, and design practices need to be aligned with the properties of the tailings. And risk assessments, they can support identification of risk, but it's essential to critically assess the mechanism. How is the dam really going to fail, and understand, is that credible? And what could you do from a design perspective to make it not credible? Because really our goal with designing a tailings dam is to not have credible failure modes. And the current dam breach analysis methods are flawed. I think, and there's good work going on as we speak. So there's a lot of people working hard at this issue of how do we incorporate the geotechnical properties and the geotechnical failure mechanisms response. And the state of practice to address challenges with the characterization of tailings continues to address understanding how do you characterize for static liquefaction, and even the response to seismic liquefaction is room to continue to develop. So thank you very much. So I'll stop sharing my screen. So I guess with the next paper, so we have, I don't know if Leonardo Moreno, are you on? I don't see you on, so maybe we'll go to the next one, which I believe is Harushi.
Okay. So I hope you guys can see my screen here.
Yep.
Okay. So I'm going to. Okay, so I'll be speaking on the dam safety. I think thanks Mr. Harvey for setting up the stage. I think it's the I guess the items which I'm going to share, I think, are kind of extension to what you mentioned, but I think more on site point of view. But prior to that, just to introduce myself, my name is Rishi. I had the infrastructure group for India operation. I worked for Walter P. Moore, which is the US Texas-based company. We have office in Pune here. and these are some of the services which we offer currently. Like I said, I think uh, dam construction is a very critical and sensitive, I think, piece as part of the civil infrastructure, and it needs to be done right. There are the life property and environment associated with it. Uh, and I think there's kind of sometimes is a perception that this is rated, the risk is rated more on large dam than on small dam sometimes in general, but I think it doesn't matter. I think it's basically either it's a large dam uh, or if it's a small dam. I think every life in general matters, irrespective is human or nature or property. Uh, right thing needs to be done on site to make sure that the dam construction is done correctly and safely. Uh, so I think just to give a perspective, the reason I guess I'm sharing this is that recently actually Walter P. Moore provided some best practices analysis to one of the state governments here, and the idea was that to provide for one of their major dam, they were preparing a she manual, and I guess the idea was to find out what are the best practices currently involved, basically preparing a menu card of the typical setup what we have, which we use the CPWD manual as a local standard here for safety. But in addition to that, is there anything which can be included, which is not there and which has been done anywhere else in the world from respective, I guess, lesson learned and all that. So, so that's what basically we did. We basically came across some of these common items, as we all know, as part of the CHI manual, as far as the dam safety goes, or worker safety goes, or construction safety goes, the means and methods, the occupational health, environmental management, what to do when you are constructing a dam upstream and downstream. So I think these are all standards, and we did came across a lot of good items, either if they were from US, from US OSHA, from UK Environmental Agency. There were some from Southeast Asia also. So there were some items which came across, but I think something which we thought was common, which was missing, I think in general was giving some guidelines on using various technologies and tools mainly uh, as part of the safety compliance. So this was kind of common I think in general for every other I think places that uh, these kind of guidelines are not currently provided. I think they are left to the contractors to pick up, and I think to be fair, I think contractors are doing right thing as best to their capabilities and capacities. But I think it would be good, I think, if we have, and this is up for debate kind of. It's like I said, we were just providing the best practices. So some of the technology tools, I mean, like right now we are talking about AI, machine learning, and all advanced thing. But I think up here we are talking about basic technology. It's a database, dam bridge maps, safety applications, flood warning, various technologies, digital documentation, all that. So I'll just walk you through some of the recommendations kind of which we suggested as the process. So the first item was dam breach map, and why this is important, I think, is that I think from construction point of view, we all do as part of a dam design process. Dam breach mapping is a standard practice, but I think what sometimes we fail to do is that we keep it more on the engineering side than on the construction side. I think it would be helpful, I think, to make sure the construction folks on site basically understand the consequences of the failure during construction mainly, uh, so that they are more aware. Uh, we basically educate them on what kind of mapping levels and evacuation routes and all those things which we are talking about when a dam breach happens. And I think we had some very recent experiences where the dam breach was not associated with the dam we were doing construction on. It was associated with something which happened upstream. So that is also, I think, those things we basically, as an engineer, designer, modelers, we sometimes don't have appreciation on it. But I think if we educate the people on site, I think they are more aware about things happening on site. and they can give the feedback, and we can make it more stringent. And on same lines, a real-time breach mapping. I mean, in general, if we know if there are going to be these days we have a lot of this flash flood events, if those kind of events are going to happen, if we have on-site, provide on-site that information that, well, this is based on the current stage of your dam design or dam construction, this kind of breach might lead to this kind of property loss or I guess downstream flooding, then I think that can also save a lot of property and damage. Another thing is communication, mainly on-site flood warning system. Again, same thing. We talk about doing this once as part of once the dam is constructed, or even once the flood has happened or anything. But I think during construction, uh, these kind of guidelines and guidance would be helpful if they are shared and connected with the site. Uh, and I think give them means and tools to monitor. I mean, there are a lot of technologies available like sensors, upstream sensors, downstream sensors, depending on what vulnerabilities we are dealing with on the site. Uh, I mean, we can also, there are also a lot of tools which we develop, like the flood map interactive tools. I mean, those kind of, we do that for the public, but I think if we make our own site folks available, or I guess more aware about these kind of tools, I think that would definitely help, because like I said, they have more appreciation of the site systems. And I think I already mentioned about sensors, I think, and sometimes I think there are also means and method available about these sensors upstream and downstream can be connected to a central unit, so that the flood warning can be sent across to the site folks upfront, and we can save some damage. Uh, Monitoring basically during construction. Again, I mean, it depends on the scale of the site also, and this is more probably applicable to a bigger site. Uh, we I think we cannot look after everyone and anyone kind of. So nowadays I think we have our mobiles, we do have our various tools I think available, which we can track individual where they are, how they are and all that. So and then again, this can be, again, all this data can be collected in a central unit, which could be helpful not only during construction, but also post construction, basically uh, to analyze any design changes. Uh, uh, and like I said, this data can be used in the future also to understand any kind of diagnostic, if during construction there were any items basically which gave any indications, I guess, of any kind of failure, then I think that will help for future diagnostics also. Uh, Database, I think this is another, again, uh, most important thing. The database relates to anything, but more importantly, this database is for the site individual, where it could include their the local information about the site individuals, contacting them during any emergency, uh, contacting them to share any messages. Uh, this could be used. I mean, nowadays we have this, like the way we are doing this presentation. I mean, it could be used for same purpose of doing connecting with your folks on site for any adverse situations. Uh, and again, I mean, this in our current digital evolution, this can all be stored in one local space. And it is not only accessible to the individuals on site, but also to the folks off site, so that all the information can be collectively resolved, and it's not limited to an individual. Uh, then there are bunch of applications available these days. I mean, I think these days application has become kind of a fad. For every small or big reason, there's somebody preparing an app. So same thing for safety. I think there are a bunch of mobile applications available which can capture, relate, document, store all the safety issues basically. Uh, uh, Incident reporting. A lot of time, a lot of on-site incident happens, so those can be reported, collected, and shared, and also I think resolved sometime on site. to this database. There are also SHE-specific, safety, health, and environment-specific apps we came across in this process, which can be used to do on-site inspections. Like all our phones basically these days come with cameras, GPS, and all that. So you basically can document any mishap, any suspicious activity, and then just relay it or share it as part of the app. That can also be very helpful. Documentation. I think we are still, I think at some places there's still a lot of paperwork going on for each and every activity. But like our company has, we have on-site documentation tool where you can take a tablet, you can document your site activities, or you can document any site observations in a particular format. Again, same thing, it can be stored and relayed to various places. So inspection and monitoring checklist. I mean, we have people going on site, especially to do this SHE inspections and all that. Same thing, that can be again, same thing, the information can be passed on pretty quickly and can be prioritized depending on the level of adversity. Transfer information, again, it doesn't require to stay on site. It can be transferred off to off-site also, to your base offices or to various clients. And again, I think we are collecting all this information so that we can make not only our current designs, construction better, but also I think use the lesson learned for the future work also. So all this information which is collected can be relayed for, or can be used for future documentation mainly. I think recently we have come across a lot of this drone application mainly. So that's another useful way, especially these dam sites are sometimes pretty huge, pretty widespread. So for example, this particular project which we were associated with it was it had a flowing water and a good depth of water, more than 3-4 meters we're talking about, and throughout the year. So the construction is going to happen within the active waters basically. So the access from one bank to another bank mainly. So if you have a technology like this, which basically can monitor activity between the banks, that I think also is pretty helpful. Definitely it needs to abide the local regulatory law, especially when it comes to drone everywhere. I think the standards and requirements are still evolving. So just need to make sure that we are following, I think, the proper protocols. It definitely, I think, it is associated with the safety aspect, the amount of data basically that can be collected, the speed with which it can be collected, the data mainly. So that also makes it useful to make decisions. We are not relying nowadays on days of data collection and come back and do analysis and make a decision. So I think in general, I think what we found out in this process, this best practices process, that with technology and with evolving technology, sky is the limit. Honestly, I mean, there are, I even mentioned, we even came across virtual reality mainly. There were some folks who are using VR also as part of this process. So I think there is no end to it, but that's a good part. I think that there is no end to it. There are options available. So I think the debate is that what are the options which can be used, what cannot be used. I think that's up for debate as part of this process. But I think at the end of the day, we all collectively, as a designers, as an engineers, as a contractor, we all want same thing. It's safety first. We want to make sure that our folks are safe, our designs are safe basically, and our designs are sustainable, and they are lifelong in general. So I think with that being said, I rest my case here, and I'll be glad to answer any questions if anybody has.
Yeah, thank you very much, Harush. That's very good, and I'm always amazed by how much how fast the technology is developing, but also that it's an extremely valuable tool, from simple things such as you mentioned, just inspections. And I think I guess the only caveat I have is that we always have to be thinking about we're not doing technology for the purpose of technology. We're doing it to help us make better decisions.
Exactly. Very well said.
And it comes into, some people believe that if you have more technology, then the dam is safe. Well, you still
True.
have to.
Yes,
So I
definitely.
think it's that tie back that's important. But
Yes.
certainly we see it all the time that, the remote monitoring, the drones, the automatic cameras, all those things really help. For example, at Mount Poly, if they had a camera on the dam, because it failed it actually failed 2 hours before people thought it failed. And water trickled over the crest of the dam for about an hour and a half before it let loose.
Wow.
And a simple camera watching the dam would have seen it.
Exactly.
So, I think those things, even simple things go left unsaid, but I think it's extremely valuable for people to be thinking just what can we do. And so I found that very interesting. So I'm not sure how the questions are handled, if they are, or I'm not. I'm new to this platform, so we'll give a few moments. If nothing happens, then we will go on to the next speaker.
Sure.
Okay, well, maybe not, or maybe at the end we'll have questions. So why don't we go on to Mohammed Ahmed, who's talking on Embrya dam breach modeling. So I'll turn it over to you, Mohammed.
Thanks very much, Harvey. Thanks a lot. I'm going to share my screen. I'm trying to share my screen, but can you see now my screen? Or?
It says you're starting to share, so let's see if it comes up. Nope.
It says there's a problem sharing the screen.
It's possible that the host can use the PowerPoint.
Yes, sir.
Okay.
So Mohammed, you could just ask them to forward when it's time.
Sorry?
It's showing now, so you could just ask them to forward when you go to the next one.
Unfortunately, I mean, it cannot view the media file on my browser, so I cannot. Let me check. Says try the desktop application. So I'm trying the desktop application at the moment.
Uh, Mr. Mohammed, are you able to share your screen or it
Sorry.
is play by me
Can
Pramost?
I mean I'm not able to share my screen for some reason.
Okay.
Uh,
So no problem, sir. I will play your PPT. Then
okay.
finish your first PPT. Say next. I will click next
Okay.
button. Okay.
Okay.
Yes, please, sir. Start.
Still loading. It's coming. Ah, yes. Okay. I can start now. Good afternoon or good morning, wherever you are, and thanks, Harvey, for chairing the meeting. My name is Mohammed Hassan from HR Wallingford. I'm going to present today a tool called Ambria Mod. It's a tool for the simulation of breaching of tailings dams. I'm presenting this on behalf of my colleagues Gregor Bitkovic and Craig Goff from HR Wallingford. Um, the tool was developed as a part of a project funded by the UK space agency, the DAMSAT project. Um, and the DAMSAT project was mainly to minimize the risk of failure of tailings dams through a number of tools. I'm going to talk about EmbriaMod today, and I'm going to give you the link of DAMSAT at the end of the presentation, so you could know more about the project. Before I start, as Harvey mentioned, this is a complex problem, and with lots of uncertainties and lots of processes that we are trying to model, breaching of a tailings dam. And this tool, we think it's the beginning. It's one step that we hope that it's a step forward, and it will be followed by other steps to make the tool stronger and stronger. Next, please. So today I'm going to talk a little bit about what is a breach and the breach failure mechanisms in tailings dams and the different of flows they can get out of a tailings dam. And then I'm going to talk about the model description and then a little bit on model validation, and I will end up with a number of conclusions. Next, please. First, what is a breach? Basically, a breach is a hole or a gap in the body of a dam or a tailings dam or a flood defense structure. Um, this hole can be over the crest of the dam or through the body of the dam, and it can happen due to a number of things. Next, please. And the issue is that through this hole or over this hole, the flow of water or tailings is the flow happens in an uncontrolled manner. So lots of water and lots of tailings can flow out of the dam, and it can cause damages, and it can cause severe consequences. Um, Next, please. So, I mean, as Harvey mentioned, there are a number of failure mechanisms. Through them, a tailings dam could fail. I mean, they could fail by overtopping, where you don't have enough capacity to accommodate the water, or the bond isn't enough. They can fail through internal erosion, where material could erode the body of the dam. They could fail to seismic effects. They could fail through a number of different mechanisms. But I mean, when we talk about the different flows out of a tailings dam, we have a number of things that we need to look at. However, there is water or not, and however the material can be liquefied somehow or not. And Harvey touched upon this, and I'm going to talk about this. So first of all, if you've got water in your tailings facility, and also the material can be liquefied, however statically or through seismic effect, then you have here water coming out of the tailings dam, also, and also liquefied material that can flow of the dam, and both of them can also erode the body of the dam. So this is there is a classification that is done, and when you move in to if the material cannot be liquefied, then you've got water, then the water can actually erode the tailings and also erode the body of the dam, and here you've got water coming out of the dam with tailings and the dam material. And then if you've got liquefied material but no water, then basically that means somehow there is a slope failure, and then the material, the tailings, can flow out of the dam depending on their degree of saturation. And then the last one, next please, is if you have no liquefied material and no water, and that would be there would be no flow. Can you excuse me? The previous slide, please. In that case, you have no flow, and this could be like a slope failure, and then there will be no flow out of the dam. The Ambria tool only models at the moment overtopping of a tailings dam, and it can model scenarios like 1A, 1B, and 2A. It doesn't model at the moment scenario 2B. So it actually models the flow of the water and tailings in 1A, 1B, and 2A scenarios. Next, please. Uh, so a bit of description of the model. So as I said, the model at the moment models overtopping. So the material, the water, the material has to overtop the dam. And the tool here models the actual breaching of the tailings dam. So it looks at how the breach would develop with time, and how much water and tailings would flow out of the dam with time as well. As Harvey mentioned, there's a difference between water breach models and tailings dam breach models. We built this tool based on a water dam breach model. The tool is called Ambria, but we added modules to take into account the tailings dam aspects within Ambria bot. So it builds upon a water dam breach tool, but it tries to take into account the aspect of tailings into this model. Um, in the model, we have assumed that you can have up to 3 layers. So you can have a water layer on the top of mud layer, and below that you can have the dam itself, the material of the dam. The water is dealt with as a Newtonian fluid. Mud is dealt with as a non-Newtonian fluid, and the dam material can only be eroded by the water and or mud. It takes into account the depth of the water, the depth of the mud, and also velocity of water, velocity of mud, and the shear stress between water and mud, and the shear between mud and the dam as well. Next, please. So again, the model takes into account the facility itself, upstream, so the pond where it's got water and tailings, and then the body of the dam as shown on the left hand figure, the longitudinal section. It also the model also splits the pond into 3 zones. It assumes that it can be modeled as a square or a rectangular with a length of L and width of W, and starts with the as shown on the left hand note, which is the width of the initial breach, and then this width goes up to the maximum width of the facility in zone 1, and then this carries on with the maximum width of the facility in zone 2, and then ends up with 0 in zone 3. So it's This is how the three zones are modeled in Umbria mud. Next, please. We try also to take into account the geotechnical aspects within modeling the breach. So we do not only take into account erosion, but we try also to take the slope stability. So this is a process where we take into the slope stability into account that the fluid, however it's mud, water, or both, can erode the breach section. And based on the shear stress on the boundaries, you get a section like that where below the mud the section is eroded, and then as the time goes by, you have like a slope which can become unstable and then collapses, and then you end up with a section like that again. And this carries on until the end of the simulation. Next, please. I mean, as I said, this model was developed within the DAMSAT project, and we have tested the model against a number of laboratory experiments, and also the results of actual tailings dam failures. I'm gonna next please. I'm gonna focus today at two model validations. The first one was against a laboratory experiment by a JAB lab, and the second one was an actual failure, which is well known, the Baumbouli failure in Canada. Next, please. So the Jablan experiment was a flume which has got one layer of oil, and this oil had a depth of 15 centimeters and a length of 61 centimeters, and then it was kept in this state, and then suddenly it was allowed to flow. Next, please. Next, please. Uh, can you hear me? Next slide, please. Thank you. So this plot shows the blue line is the initial profile of the oil, and after about 2 minutes, the model results. And the green line is the profile predicted by Ambria Mud, and the purple points are the experiment's result. And as you can see, the results of the model are pretty close to the experiment results. In this model validation, we try to test the model against a non-Newtonian fluid and see how it can predict this behavior. And then, next slide, please. We then did validation against actual failure of embankments, and the well-known Mount Boley test, the well-known failure of tailings dam, the Mount Boley one. The The Mount Bowie failure took place in 2014 within this perimeter embankment, as shown in the figure. Next, please. The dam, when it failed, was about 40-meter high. Next, please. And the crest dropped by about 3.3 meters, as you can see here. The figure on the top is the profile before failure, and the figure at the bottom is the profile after failure, and the crest dropped by about 3.3 meters, and about 21 and 25 million meter cube of water and tailings were released after the failure. There was no fatalities for this case, but it caused very severe environmental consequences downstream. Next, please. So some of the results that you can get out of the dam can predict the water outflow hydrograph. This is shown by this blue dotted lines, and it also can predict the outflow of tailings plus eroded material from the dam. In this case, the peaks were almost more or less the same for water and the tailings for this case. Next, please. You can also have a look and see the profile of water and the profile of tailings with time, and also the profile of them. So the black dashed line is the initial profile. Sorry, is the profile before failure, and then the black dotted line is the profile after failure, and the blue and red and black lines are the water, mud, and dam profile after 4.5 hours of failure. So this also, you get the progression of the different levels of water, mud, and dam with time. So when we come, next please, next slide please. So when you compare the results of what was recorded during the failure and the estimation of the model, next slide please. Uh, Looking at different parameters like the tailings volume that was released, the final breach width, the average observed width of breach, and the time to peak, and the total time failure, you could see that the model reasonably predicted those parameters for this case. Next, please. So I finished with a number of conclusions. So what I would say that Ambria Mod is a tool that is physically based. It's got um, uh, um, uh, capability, it's got a capability to predict the outflow rates of water and mud, and also how the breach would grow with time. It considers the interaction between layers, water, mud, and the dam itself. Next, please. It has been tested against laboratory and actual failures, and we think the results showing good agreement with both and are reasonably presented. And as I mentioned, this is just the beginning. We know that there are lots of things that need to be added to this tool, and we are hopefully with time and with the help of the community, we can improve further and validate the model so it can be a tool that can be used by the industry. Before I finish, I would like to acknowledge and thank the UK Space Agency and the DAMSAT project partners for helping out in developing this tool. Please visit www.damsat.org to know more about this project. Next, please. Myself, I'll be more.
Well, thank you very much, Mohammed. And certainly, as you can see, dam break is dear to my heart as well. So that was a very good talk. And I was interested to see how you were able to have some simulation of Mount Poly. And I will have a question in a minute about it, but I think it is good to be recognizing that these mechanisms of water and tailings and what's happening, and having some simulation, being able to model, in this business, to have a model that's within 50% is pretty remarkable. Some can be out several 100%. So I think it is that is good. And now a question that I have would be, I just wasn't sure. If you took this same model and didn't put tailings in, what would have happened? Would be one question. And then just what properties of the actual tailings went into, and you don't have to get into details, but just in general, what properties of the tailings were input into the model.
Thanks, Harvey. So if we just use the Ambria breach model, it would only erode the tailings. So it wouldn't actually flow any of the tailings. So basically, if we have no tailings processes and we used a water dam, so water dam break model or the Ambria model, it would only material. So I hope this actually answers your question. The second one,
Yeah.
yes,
No,
we have.
no, no.
The second question, we have taken the tailings properties into account. So we have taken the yield stress, the viscosity into account. As you mentioned, these are difficult to estimate. So we have tried to use the best information available on those tailings properties. We have also taken into account the erodibility of the tailings, the friction angle, and cohesion of the tailings to be able to calculate the technical failure. So these are the properties at the moment that are taken into account.
Yeah, well, certainly it appears that your model is, which is in this case very appropriate because it is primarily water transported tailings. I mean, the volume of water was similar to the volume of tailings in total that got released. So it is helping to at least kind of support that. Primarily, it's the water eroded tailings which is being released in this case versus a Brumadinho or a Fundal where you're getting liquefaction of all the tailings. Okay, thanks. That was good. Yeah, I can see I'll have to contact you and your colleagues a bit more and have some further discussion. So it was
Yeah,
refreshing
sure.
to hear this.
Yes, you are welcome. You are welcome.
Are there questions from anybody else or comments? I think if not, then maybe we'll close the session. Certainly, it's been a very informative session, and I think.
Excuse me, sir.
Oh, yeah.
I have some questions in outbox.
Okay.
I will send
Thank
you. I will send you. Just a minute.
We're on chat. Oh, I see. We have person standing in for Breno Castillo. Okay, so that's the. So we do have another presentation. So are you able to share your presentation?
Sir, no anyone next presentator.
Okay. So they go on to the questions. There's a question here. Could you explain the tailings dam failure on the fault zone, how to mitigate the failure? And difference between water dam and tailing dam based on the geometry. I'm not sure if I understand the question. Because I'm not sure what the fault zone is. I assume if you're placing a tailings dam over a fault is the question. And the difference between the water dam and tailings dam based on the geometry. If you go with the downstream tailings dam, then they're exactly the same. If you go with a center line, the structural portion of the dam would be similar to the center line downstream side of a water dam. An upstream dam, you would have tailings directly on the foundation, if that's the question. I could comment on the first one. I'm not sure if I understand it, but explain the tailings dam failure on a fault zone. Certainly, if your dam is over a fault, you're basically the seismic loading from it would impart loads that you'd have to be designed for. And with respect to deformations along faults, it depends on the type of tailings dam as to how much deformation it can get. I know I've designed cyclone sand dams in high seismic areas where, because the cyclone sand dams are basically just one large body of sand, they can take tremendous deformation without failures. So there's no more questions. So I think if there's no more questions, and I don't know if we're able to show the view of inside tailing dam paper. I guess that would be up to, I guess, the co-host or the host. Is it possible to show that? If not, then we'll conclude the session.
What, sir? What you need to say?
Well, there's a question there. A person is standing by to present the paper inside, view inside tailing dam. Reno Castillo, is he able to present?
Just a minute, sir.
Reno, were you able to sign into the meeting request that we had for the organizing part? Because I think it's a different web link than the one that you're on.
Sir, I have Breno Castling, Breno Castlo PPT. Can I play? But they,
Is
but
he able to present?
no, he's not able. He's not present.
Okay.
So no anyone other presenter here.
Yeah, Brandon, I don't know what the mix-up was, but it doesn't look like you're able to present.
Okay, no problem.
So that's unfortunate. Um, but thank you for participating anyway. So I guess to maybe I'll just wrap up the session. It's been a very informative session, and actually, the three talks were fairly well aligned, even though it wasn't planned that way. And I think that certainly tailing dam safety is on everybody's mind these days. There's tremendous efforts going in, both from the governance side as well as the technical side going into tailing dams. And the more we can understand tailing dams, the more we can educate and communicate to people what they are, how they're designed, how do you manage them, what are potential consequences if you're not designing them appropriately and managing them appropriately. And certainly the failures that we've seen over the last 10 years do highlight that it's a very important issue. And there's many bodies doing a lot of very good work with it. So I'd like to thank, excuse me, apologies, Harushi, for your talk on the technology and monitoring, and it's a fascinating area, and certainly I see it every day. It just gets continued more use, and it helps to communicate things. It also reduces human error by having things documented electronically versus writing down and forgetting something. So I think all these systems work towards making dams safer and understanding when we're monitoring them, the benefits of monitoring and making sure that they are aligned with the principal goal of dam safety and protection of the workers and the environment. And certainly dam breach modeling is, there's a lot of work going on, and we're involved in Canada with the Can Breach program, which is a consortium of universities and industry partners looking at research into dam breach. I think our own company are doing our own research as well. So there's a lot of good research going on with dam breaches and understanding them. Because certainly it's not just a question of taking the water dams and applying them to tailing dams. It's more complicated than that. But certainly we're moving in the right direction. So I'm going to thank the speakers and thank the host, and thanks all the audience for joining us today in this session. And either have a good morning or a good evening, whatever time zone you're in. So thank you very much.
Thank you, Mr. Harvey.
So I'll stop sharing. Thank you.
Thank you.